These are the notes on the first section of Chapter 11. Chapter 11 is a chapter called Areas of Plane Figures. And in the first section, we're going to be talking about the area of a rectangle. Remember, a rectangle is simply a parallelogram with 4 right angles. We're also going to talk about the area of a square here, and a square is just a special rectangle. It's a rectangle with 4 congruent sides. The book makes a distinction between the area of a rectangle and actually finding the area of the region inside the rectangle. So technically we're finding the region of areas inside of figures. Let's talk about area just for a second. Area is that amount of space inside the figure. And so on the left I've got one small little square figure here, a 1 by 1 figure. And so this would be a figure of 1 square unit, all right? So this is 1 square unit. If that unit happened to be, let's say, centimeters, then that would be 1 square centimeter, or the notation is 1 cm for centimeters with a little exponent of 2 there. So that's 1 square centimeter. So one way to find area is to count how many of those little square centimeter spaces or square unit boxes there are in a figure. All right, in this section there are 3 postulates. We're going to start off with postulate 17, which says that the area of a square is the square of the length of a side. All right, so take a look at the square I've got here, which is a 4 by 4 square. So one way to figure out the area is count how many of those little square spaces or boxes are there in that figure. And if you count them, you'll see that there's a total of 16. Okay? An easier way would be, of course, to count how many rows there are and how many columns there are and multiply the two together. So 4 times 4 would be equal to 16 also. And that leads us to the formula for the area of a square, because 4 and 4 represent the lengths of the sides, so we're multiplying side by side, which would be side squared. So the area is equal to s squared is the first formula. I'm going to box that, and you need to remember that one from this section. All right. The second postulate, postulate 18, is called the area congruence postulate. And it says if 2 figures are congruent, then they have the same area. Think back about our definition of congruent. Congruent means same size and same shape. Well, it's kind of common sense. If they're same size and same shape, then they're going to have the same area. All right? So I've drawn a couple of triangles here, triangle ABC, triangle DEF, tried to make them look like they're congruent. And if in fact they are congruent, then the area of triangle ABC is equal to the area of triangle DEF. Note that the converse of this is not necessarily true. If we have 2 figures that have the same area, they don't necessarily have to be congruent. For example, we could take a circle and have draw a circle that has an area of, let's say, 4 square units, and then draw a square that has the same area. But certainly those two are not congruent. Circles and squares are not the same shape or same size. All right. Postulate 19 is called the area addition postulate. This is a pretty simple idea as well. It says the area of a region is the sum of the non-overlapping parts. So I've drawn a couple of figures here. On the left, I've got a quadrilateral ABCD. And this is not a special quadrilateral. We don't have a formula for the area of it, but if we needed to calculate the area, we could divide it into 2 regions, 2 triangles, as I've shown in the diagram, called region 1 and region 2. The area of that quadrilateral, therefore, would be the sum of the area of region 1 plus the area of region 2. The same is true for the trapezoid on the right. I've drawn a trapezoid. We could find the area of that trapezoid by dividing it into a triangle, a rectangle, and another triangle. So if I want to find the area of that trapezoid, I could add up the 3 regions, 1, 2, and 3, and that would give me the total area of the trapezoid. Later in this chapter, we'll actually have a formula for the area of a trapezoid. But right now, we can do it by this using this postulate 19. All right. This brings us to the theorem 11.1, which says the area of a rectangle equals the product of its base times height. So I've drawn a rectangle here, and the goal is to find the area of the shaded region in there. And I've labeled the bottom the base and the vertical side the height. Those are interchangeable. The base could be the side and the height could be the bottom, just depends upon which way you look at the rectangle. But at any rate, instead of counting up all the little square boxes in there, we saw in that first example with the square that we multiply the number of rows by the number of columns. So that brings us to the formula. The area is equal to base times height for a rectangle. Okay? For this particular one, it looks to me like the height is 4 and the base is 1, 2, 3, 4, 5, 6, 7, 8, 9. So therefore, this would be the area of base times height, which is 9 times 4, or 36. All right, in my next example, I've got a couple of rectangles side by side, and the goal is to find the area of the shaded region. So there are two nice ways to do this. One is to separate it into those non-overlapping regions. So I've got a big rectangle on the right, which looks like it would be 6 by 5, or have an area of 30, okay? And then the one on the right is 2 by 3, which would have an area of 6, okay? So if I add those two up, 30 plus 6, I get a total area of 36. The other way to think about this, it's kind of a neat idea, is extend these sides to make one whole big rectangle, which would be 8 by 5. So 8 times 5 would be 40. And then take that 40 and subtract out the missing little square in the lower right-hand corner, which is 2 by 2, 4, and that gives us the same answer. That's kind of a nice technique that will come in handy every once in a while. Find the area of the whole thing and then subtract out the part that you don't want. Okay, my next example is a chart, and I'm doing this because you're going to see some charts in the homework section that you take a look at tomorrow. And so this chart represents the base, the height, the area, and the perimeter for a rectangle. B, H, A, and P stand for base, height, area, and perimeter. And the goal here is to fill in the empty boxes. Okay, so first of all, I need to get out my calculator, and we'll do some calculations here. Okay, and so first of all, I've got a base of 18 and a height of 3. So the area would be 18 times 3, which would be 54. Okay, pretty easy, right? Area of 54. Now the perimeter, remember, is the distance around the outside. So the distance around the outside would be 2 of those bases plus 2 of those heights. So with my calculator, I want 2 times 18 plus 2 times 3. And that would give me a perimeter of 42. Okay? And the second one, same question, but a slightly different twist. I'm given the base and I'm given the perimeter. Okay? So I need to find the height in the area. So it's going to require a little simple algebraic calculation here. That if I take 7.5, which is the base, and I take 2 of those, plus 2 of the heights, that gives me the perimeter of 39. All right? So 2 times 7.5 is 15. If I subtract the 15 from 39, I get 2h is equal to 24, and therefore h is equal to 12. So I know the height is 12. All right? And so now I can figure out the area, of course. That would just be the 7.5 times 12, base times height. 7.5 times the 12, and that gives me an area of 90. All right. In the third column, I'm given the base of 25 and the area is 150. So this is a similar idea. I know that base times height is area, so that's going to be 25 times the height is equal to 150. So if I take 150 and divide by 25, that turns out to be 6, right? So the height is 6. And then the perimeter would be 2 of the bases plus 2 of the heights. So let's see if we can do this in our head. 2 bases would be 50, and 2 heights would be 12, so that would give us a total of 62. All right, and then finally the fourth column is an algebraic column. We're not going to be able to do numbers here. We're going to have to do this algebraically. All right, so I know the base is 4x, and the height is 4x minus 1. So therefore the area would be 4x times 4x minus 1. So if I distribute there, remember your algebra days, you distribute. 4x times 4x is 16x squared, and 4x times 1 is a minus 4x. All right? The perimeter would be 2 of those 4x's plus 2 of the 4x minus 1's. So 2 of the 4x's is 8x. 2 of the 4x minus 1 is 8x minus 2. So therefore the perimeter would be 16x minus 2. All right, and finally, my last example, I'm going to circle these up here just to be consistent. And then finally, my last example is I'm given this rectangle with a diagonal drawn, and the diagonal makes an angle of 25 degrees with the base. and the goal is to find the perimeter of the rectangle. So I'm going to label this H over here, and I suppose if we could find the H, then we'd take 2 of the H's plus 2 of the 9's, the base is 9, 2 of the H's plus 2 of the 9's, and that would give us the perimeter. So we're going to use trigonometry to find that height. All right, so in this triangle I've got the angle, and the height is the opposite side, I'm looking for that, and the base 9 is the adjacent side. So opposite and adjacent would mean we're using the tangent trig function. Okay, so we're going to say that the tangent of 25 is equal to the opposite over the adjacent. And then I'll multiply both sides by 9, so that's going to be 9 times the tangent of 25, and that gives me the height. So with my calculator, I go 9 times tan of 25, and that is approximately 4.2. Okay, I'll write this down here just to remind us. But I'm actually going to use the whole thing. So I'm going to go times 2. Notice when I press times, it takes that last answer, and then times 2, plus 2 times 9. That's 2 of the bases. Press enter, and that gives me a perimeter of approximately 26.4. So the perimeter is equal to 26.4, whatever kind of units that we're talking about here. Okay, that concludes the notes on this section, chapter 11, the first section.